Signals and Systems, Laplace Transforms, Part 1, Series on Signals and Systems, Lecture number 4.11. This is the second part, continuation of the first part. In this part, the focus is mainly on initial value theorem, final value theorem, transform of causal periodic functions, ROC of transforms, and some other interesting features of transforms also. After having some initial introduction to properties of Laplace transforms, we consider two theorems. These are highly useful, widely used in the analysis of systems with the Laplace transforms. They are initial value theorem and final value theorem. Initial value theorem and final value theorem. What are these theorems? A small introduction is being given here. If f of t and its first derivative are Laplace transformable, then f at 0 plus function value at the origin when approached from positive time side. That is the meaning of f of 0 plus. It is equal to limit s tends to infinity sfs. This is initial value theorem. The reason for it being called initial value theorem is that it gives initial value of the signal. Second one is called final value theorem. The reason is it gives the ultimate or final value of the signal, f infinity. According to final value theorem, f infinity or f as t tends to infinity is limit s tends to 0 sfs. This one. These two are, as already mentioned, highly useful, widely used. Note that the right hand side of the above equations may exist without the existence of left hand side, that is f0 plus or f infinity. Thus, the theorems should be applied only when f0 plus or f infinity, they are available, they are existing. These theorems are useful to determine the initial and final values of an unknown function f of t if its transform fs is known. Now we consider some transform pairs, popular transform pairs, widely used transform pairs, or transforms of some standard signals. We begin with the Laplace transform of impulse function. Laplace transform of unit impulse function is 1. Next we consider step. Laplace transform of unit step function is 1 by s. Next we consider Laplace transform of t power n u of t. It is n factorial by s power n plus 1. Then we consider another function t power n e power at u of t. For this, Laplace transform is n factorial divided by s minus a power n plus 1. Here we consider trigonometric and hyperbolic functions. Laplace transform of sine omega naught t u of t. It is omega naught by s square plus omega naught square. Similarly, for cos omega naught t u of t, for this transform is s by s square plus omega naught square. Hyperbolic functions, in case of sin h of at u of t, for this signal Laplace transform is a by s square minus a square. In case of hyperbolic cos function of at u of t, for this Laplace transform is s by s square minus a square. Now we consider Laplace transform of causal periodic signals. What are causal periodic signals? By definition, periodic signals are signals that exhibit certain kind of periodicity, certain kind of repetitiveness in their nature, and they extend from minus infinity to plus infinity. Causal periodic means periodic signals, but they exist only from 0 to infinity. 0 to minus infinity, in that range, they are 0. After having some idea regarding the nature of causal periodic signals, now here is being explained a method by which one can determine their Laplace transform. A causal periodic signal of period t can be represented as a sum of the function in the first seconds and this same function delayed by t, 2t, 3t by seconds. If we designate the first cycle of f of t as f of t naught, then okay. I will give an example. With this example, understanding will be good. This is an example for causal periodic signal. On negative time side, it is 0. So it is causal, and periodicity is there in the signal, therefore it is periodic, hence it is causal periodic. To find Laplace transform for this signal, it can be divided into several signals. This is first one, second one, third one, fourth one. The first one, which is near to the origin, it can be designated as f of t naught. Second one, this can be designated as f of t naught minus t. Third one may be designated as f of t naught minus 2t. Like that, one can designate all the cycles and they can be added to get the actual causal periodic signal. Now, for a Laplace transform of causal periodic signal becomes sum of Laplace transforms of f of t naught, f of t naught minus t, f of t naught minus 2t, etc., etc. He is explaining, it is being explained here, the procedure. Taking the Laplace transform both sides, f of s is Laplace transform of f of t. It is equal to f naught of s plus f naught of s e power minus st plus f naught of s e power minus 2st, etc., etc. So it can be written in a compact form, f of s equal to f naught of s into 1 plus e power minus st plus e power minus 2st plus etc. e power minus nst plus. So this can further be simplified as f of s equal to f naught s by 1 minus e power minus st. So this is the expression for Laplace transform of a causal periodic function or signal. Now we consider another aspect of Laplace transform. Let us suppose there is a signal and it is two-sided. Here is a signal which is two-sided. It is there on positive side, it is also there on negative side. Then how to get its Laplace transform without doing bilateral or with unilateral transform? Signal is two-sided, appropriate transform is bilateral. So we need to calculate bilateral transform. The point is how to get this bilateral transform of this particular two-sided signal with unilateral transform. This aspect is explained here. When a two-sided signal is given, the following procedure is useful to find its transform. Split the signal into right and left-sided signals. Let us suppose f of t is the signal, given signal, two-sided signal. It can be written sum of two signals, one right-sided, another left-sided. F of t, u of t. Here u of t represents step function. F of t, u of t, this is right-sided function, right-sided signal, right-sided part of the signal, and f of t, u minus t, this is left-sided part of the signal. First one, here it is designated as F1, second one is designated as F2. So F1 is right-sided, F2 is left-sided signal. Find their Laplace transforms. F1 of S. It is Laplace transform of F1 of t. It can be obtained by applying Laplace transform to F1 of t. F2 of S, here it is Laplace transform of F2 of minus t. Notice, it is not F2 of t. It is Laplace transform of F2 of minus t. As it is, F2 of t is left-sided. When you consider minus t, F2 of minus t, then it becomes right-sided signal. So, unilateral transform can be applied without any difficulty. Third step is add the two transforms after inverting the second one. This addition results in a Laplace transform, which is the Laplace transform of the original signal f of t. Now, in this slide, Laplace transform is connected to Fourier transform. The connecting relation is given here. If the signal x of t is absolutely integrable, Fourier transform of x of t is equal to Laplace transform of x of t with s equal to j omega plus Laplace transform of x of minus t with s equal to minus j omega. So here Fourier transform, Laplace transform. These two are being connected. If the signal x of t is positive time and absolutely integrable, then Fourier transform of x of t is simply Laplace transform of x of t with s equal to j omega. So first relation is more general. Second relation is for positive time signal. Now we consider an important aspect of Laplace transforms, that is ROC, which stands for region of convergence. First, let us try to understand what is region of convergence. It is a region in the S-plane which represents the values of S for which the transform exists. In the beginning, it is mentioned that one can calculate the Laplace transform using the available defining relations for a signal. But the fact is, the transform exists only for certain signals and only for certain values of S, that is complex frequency. These values, when located on S-plane, they form into a region. This region is called region of convergence. Note, region of convergence depends upon the signal function. It means it varies from signal to signal. To understand more about this region, consider the Laplace transform of a signal, general signal x of t equal to e power at. E power at is defined for all t. Now, applying definition, Laplace transform of e power at is integral 0 minus to infinity e power at e power minus st dt. Performing integration results in minus 1 by s minus a e power minus sigma minus a t cos omega t minus j sin omega t. Limits t equal to 0 minus to t tends to infinity. Now, one can notice in the above expression, as t tends to infinity, the expression assumes infinity or minus infinity when real s is less than a, and the expression becomes undefined when real s is equal to a. The expression is 0 when real s is more than a. So there are two situations where expression becomes meaningless. It is meaningless when real s is less than a, and also when s equal to real s equal to a. Thus, the transform is not defined for real s less than or equal to a. So transform do not exist for real s less than or equal to a. However, we can notice when real s is more than a, transform exists and it is equal to 1 by s minus a. So we can conclude with this understanding that only for certain values of s, transform exists. Transform is meaningful. These values, when located on S-plane, they form a region. That region is called region of convergence. S-plane appears like this. It is horizontal axis representing sigma, vertical axis representing j omega. A point in this plane represents a specific value of s. As it represents different values of s, it is called S-plane. ROC is certain region in S-plane like this. Now some points, important aspects pertaining to ROC. The ROC in general exhibits certain properties. They are being mentioned here. ROC of a signal x of t consists of strips parallel to j omega axis in the S-plane. Vertical axis is j omega axis, horizontal axis is sigma axis. ROC in general consists of strips parallel to j omega axis like this. Strips. This is one strip parallel to j omega axis in the S-plane. If signal xt is of finite duration and absolutely integrable, then ROC is entire S-plane. All values in the S-plane, they are in the ROC. If signal x of t is right-sided, if it exists only for positive values of time, then the line real s is 0, both is in the ROC. If signal x of t is right-sided and the line real s equal to sigma naught is in the ROC, then all the values for which real s more than sigma naught will also be in the ROC. If the signal is left-sided and the line real s equal to sigma naught is in the ROC, then all the values for which real s less than sigma naught will also be in the ROC. If the signal x of t is two-sided and the line real s equal to sigma naught is in the ROC, then the ROC will consist of a strip in the S-plane that includes the line real s equal to sigma naught. So here 3 points are being mentioned, each one corresponding to left-sided, right-sided and two-sided. First consider right-sided. What he says is, there is a signal, it is right-sided and line is there denoting real s sigma naught. That line will be like this. Here it is sigma equal to sigma naught. If this line is in the ROC, then All values for which real S is more than sigma naught will also be in the ROC. It means this entire region, which is right side of sigma equal to sigma naught. This is ROC of the right-sided signal, or when the signal is right-sided. If the signal is left-sided, then the entire region which is left of the line sigma equal to sigma naught, it is ROC. If signal is two-sided, then ROC consists of a strip in the S-plane that includes the line real S equal to sigma. It means a strip like this. It is a strip which includes the line. It is ROC, the signal. Some more properties. If the Laplace transform x of s is rational, what is a rational? Rational function. Ratio of two polynomials is a rational function. If x of s is a rational function, then the ROC cannot contain any poles. The ROC is bounded by poles or it extends to infinity. So these 2 points, they are regarding ROC being mentioned with reference to transform x of s. In the previous slide, information regarding ROC, nature of ROC, behavior of ROC, properties of ROC, they are being mentioned with respect to time domain signal x of t. Here, properties of ROC is being mentioned with respect to x of s in these 2 points. If x of t is right-sided, the ROC is the region in the plane to the right of the rightmost pole of x of s. If x of t is left-sided, the ROC is the region in the plane to the left of the leftmost pole of the transform x of s. So in these 2 slides, a good amount of information along with a definition for ROC pertaining to Laplace transforms is provided. With this, we come to conclude second part of this session as well as the total session. Before closing, let us recollect the important points that are considered. Definition of Laplace transform, both bilateral and unilateral, and difference between them, all are given. And then various properties of transforms, pairs, transform pairs, they are given. And then we move to the region of convergence. Hope you have benefited out of this session. We meet again in another session with a new topic soon.